We've been doing direct proofs primarily concerned with the parity of a number. Now we're going to take a look at some other math ideas and do proofs connected to those. So the first idea we're going to look at today is the idea of divisibility of integers. So if we have two integers a and b with a not equal to 0, we say a divides b, and we write it with that vertical bar there, if b equals a times c for some integer c. So basically the idea here is we can take b, divide it by a, and we end up with a whole number c when we do that. So we're going to write it though as b equals this product ac when we're working with it, because it's just a cleaner way to think about it. If a does not divide b, then that vertical bar, we put a slash through it, the same way we do when we say something's not equal to something. All right, so here's some examples really quick. We've got 7 divides 21, since 21 equals 7 times 3, and 3 is an integer. 6 divides negative 30, since negative 30 equals 6 times negative 5, and negative 5 is an integer. 4 does not divide 42, since there's no integer that I can multiply 4 by to get 42. I would have to multiply by 10.5, and 10.5 is not an integer. So if a divides b, then a is the divisor of b, and b is a multiple of a. So that's some vocabulary words that we're going to be throwing around. So here's an example of what a divisibility proof might look like. We have a, b, and c are integers. A is not 0 and b is not 0. And then we're going to prove if a divides b and b divides c, then a divides c. So we have a, b, and c are integers already. We've got a and b are not 0 already. And now we're going to assume the thing that goes with the if statement. So we're going to assume a divides b and b divides c. And now we're going to use the definition of divisibility, and we're going to say, all right, well, if a divides b, that means that b equals a times x for some integer x. And if b divides c, that means that c equals b times y for some integer y. And then we're going to combine these ideas. So we have c equals b times y, and then we have b was a times x. So we'll plug in a times x for the b, and we'll end up with c equals a times x times y. Now, x times y is the product of two integers, which we know is an integer. So since x times y is an integer, we have that c equals a times an integer, so a divides c. Now, these proofs can get a little bit more complicated, and sometimes we need to make some other steps along the way. So here's an example of one where we get x is an integer, and we're asked to prove if 2 divides x squared minus 1, then 4 divides x squared minus 1. So we're going to assume that 2 divides x squared minus 1, that thing that's paired with our if statement. So that tells us that x squared minus 1 is going to equal 2y for some integer y. So now I have this equation, x squared minus 1 equals 2y, that I can work with and I can move stuff around with. So if I add 1 to both sides, I find that x squared equals 2y plus 1. Well, 2y plus 1, I recognize that. That's an odd integer. So x squared is an odd integer. Well, now I know that the only way that I square an integer and end up with an odd integer is if the integer I'm squaring is also odd. So I know that x is also an odd integer. So now I have that x is going to be 2 times z plus 1 for some integer z. That's the definition of x being an odd integer. So I'll go back to this idea of x squared minus 1, this expression that I was working with, and I'm going to plug in 2z plus 1 for x. So I'll have 2z plus 1 squared minus 1 is the same as this expression x squared minus 1. And when I square this, I end up with 4z squared plus 4z plus 1 minus 1. And when I do some simplification here, I find that I've got 4z squared plus 4z, which is 4 times the quantity z squared plus z. Now, since z is an integer, and all I'm doing is squaring it and adding it, I'm squaring an integer and adding integers. Z squared plus z is an integer. So I have that 4 divides x squared minus 1 because x squared minus 1 equals 4 times an integer. Now, here I have a slightly different proof that I'm trying to make related to divisibility. So I have n as an integer, and I'm asked to prove that if 5 does not divide n squared plus 4, then 5 does not divide n minus 1, and 5 does not divide n plus 1. Now, it's not always the case, but it's often the case that if I'm using the word not in all the parts, so my P statement, 5 does not divide n squared plus 4, has a not in it, and my Q statement has a pair of nots in it, 5 does not divide n minus 1, and 5 does not divide n plus 1. Oftentimes, when nots are that prevalent, I want to flip over and think about the contrapositive, because that's going to make it a slightly less cumbersome way of thinking about the thought. So I'm going to look at the contrapositive. So I'll have 5 divides n minus 1, or 5 divides n plus 1. That's the negation of my Q statement. And I'm going to be looking to prove that 5 divides n squared plus 4, the negation of the P statement. So let's assume the negation of the Q statement, 5 divides n minus 1 or 5 divides n plus 1. And we need to break this into two cases. So let's look at the first case where 5 is going to divide n minus 1. So I have n minus 1 equals 5 times a for some integer a. Now, I have an equation here that I can move stuff around, so I have that n equals 5a plus 1. So if I take a look at n squared plus 4, that expression that I want to know if it's a multiple of 5, well, since n is 5a plus 1, n squared plus 4, I'm plugging in 5a plus 1, so I square that. I end up with 25a squared plus 10a plus 1, and I still have my plus 4. So simplifying this, adding the 4 in, I actually end up with this is equal to 5 times 5a squared plus 2a plus 1. So I have that n squared plus 4 equals 5 times this integer, 5a squared plus 2a plus 1. So that means that 5 divides n squared plus 4. So in this case, I've now proven that if 5 divides n minus 1, regardless of whether 5 divides n plus 1 or not, then I have my result. Now in the second case, I'm looking at if 5 divides n plus 1, and I want to show the same thing, regardless of whether 5 divides n minus 1 or not. So I'm looking only at this. So I have n plus 1 equals 5b by the definition of dividing. And now I have this equation that I can manipulate. I end up with n equals 5b minus 1. And we follow basically the same pattern here. And we end up finding that 5 in fact does divide n squared plus 4. So now with these two cases, I've now shown that the contrapositive is true, and therefore the original statement must be true since they are logically equivalent. Now, I want to go back to the definition of even and odd integers really quick. So remember when we define an even integer, we say n is even if n equals 2q for some integer q. And what this is basically the definition of 2 divides n, right? So whenever we're talking about even, we are saying, if I tell you that an integer is even, I'm telling you that 2 divides that integer. Now, if the integer is an odd integer, we know that 2 does not divide it. And in fact, we write it as 2 times an integer plus 1. Since integers are either even or odd, when we divide by 2, we can see that the remainders, all we can get is a 0 and a 1. Similarly, if we divide by 3, our possible remainders are 0, 1, and 2. So I can actually think about integers also as being able to be written as multiples of 3 plus 1, and multiples of 3 plus 2. So I can break it down that way, and it's really just following this even-odd pattern that I've set up, but thinking now in terms of divisibility. Similarly, I can do this with 4, I can do this with 8. I just always have to have all the possible remainders tagged on as possible ways that I could write my integer. And this proof's helpful in some types of proofs that we do. So let's take a look at this example here. We have x and y are integers. Then we want to show that 3 divides x and y if and only if 3 divides x or 3 divides y. So let's first look at this direction, right? So we're looking at 3 divides x or 3 divides y. So if 3 divides x or 3 divides y, then 3 divides xy. So we're going to assume the thing that's with our if statement, 3 divides x or 3 divides y. And because x and y are both integers and we're looking at 3 dividing either one of them, and there's no way we can really distinguish between them in a meaningful way that we need to, so we can say without loss of generality, we can assume that 3 divides x. So we have x equals 3z for some integer z. So now xy is going to equal 3z times y, which equals 3 times zy. And zy is an integer, so 3 divides xy. Now we need to look at if 3 divides xy, then 3 divides x or 3 divides y. Thinking about 3 dividing the product and doing anything with that is very complicated. So we're going to look at the contrapositive of that statement. So we're going to look at 3 does not divide x and 3 does not divide y. Then we're looking to prove that 3 does not divide x, y. So since we're assuming 3 does not divide x, then we know that x is either 3 times an integer plus 1 or 3 times an integer plus 2. We know there's a remainder when we divide by 3. Now, similarly, we know the same thing for y. When we divide it by 3, we're going to have a remainder. So for some integer q here, we've got y is going to be 3 times that integer plus 1, or y is going to be 3 times that integer plus 2. So now what we have to do, we have 2 possible values for x and we have 2 possible values for y, and we need to look at every possible combination of those. So that leads us to have 4 cases. So in the first case, we're going to look at both of them being 3 times an integer plus 1. So we basically write our product, x times y, as 3 times p plus 1 times 3 times q plus 1. We do some arithmetic, some simplification, we factor out a 3, and we have a remainder of 1. And that tells us that x times y is equal to 3 times an integer plus 1. And that plus 1 tells us that 3 does not divide xy. Doing the same exact steps, basically, we can do the cases where x equals 3p plus 1 and y equals 3q plus 2. The case where x equals 3p plus 2 and y equals 3q plus 1. And the case where they both equal 3 times an integer plus 2. All right. In addition to divisibility, we can think about congruence of integers. So when we say that 2 integers are congruent, so we say A is congruent to B modulo in we write this with that equivalent, the 3-bar equal sign looking thing, right? So A is equivalent to B mod N. We write it that way. And what this means is that N is going to divide the difference, A minus B, right? Or the idea here is when we divide A by N, B is the remainder that we have. But it's a lot easier, a lot more straightforward, a lot more useful to think about it as N dividing the difference, A minus B. So some examples here, I have 17 is congruent to 2 mod 3. I have 17 is congruent to 2 modulo 5. I have 14 is not congruent to 4 mod 6. All right, so we can see that 17 minus 2 is 15. 15 divided by 3 is an integer, so we're good. 15 divided by 5 is an integer, so we're good. 14 minus 4 is 10. 10 divided by 6 is not an integer, so that division does not work. And we don't have that difference is divided by our 6. So let's take a look at an example of a proof with congruence. So we have A, B, C, D, and N are all integers, and we're going to have N is greater than or equal to 2. The reason for that, when we take modulo 1, then we're just taking the number itself. There's no point in actually looking at that congruence. So our modulos will always be 2 or more. So we have if A is congruent to B mod N and C is congruent to D mod N, then A plus C is congruent to B plus D mod N. So we're going to use the definition idea here. So we're going to first assume the thing that's with our if statement. So we've got A is congruent to B mod N and C is congruent to D mod N. We're assuming that. So then, by the definition of this congruence deal, all right, I have A minus B equals N times X, and C minus D equals N times Y, where X and Y are integers. All right, so now what I'm going to do is I'm going to take those two equations that I had, my A minus B equals NX and C minus D equals NY. I'm going to add the two left-hand sides together. I'm going to add the two right-hand sides together. And that's going to give me A minus B plus C minus D equals NX plus NY. Now, doing a little bit of maneuvering, I can group my A plus C together, and I can group my minus B minus D together and factor out the minus. So I end up with A plus C minus the quantity B plus D equals N times X plus Y. Now X plus Y is an integer. By the definition of divides, I have N divides A plus C minus the quantity B plus D. Now by the definition of congruence, I have A plus C is congruent to B plus D mod N. And that's what I was looking to prove. Now, here's an example where I have the same setup. I have A is congruent to B mod N, and C is congruent to D mod N. That's what I'm going to assume. And I'm going to show that AC is congruent to BD mod N. So again, I do the same setup. I use the definition of congruent, and I say A minus B equals NX, C minus D equals NY. And then I had the pieces across, so I actually have A and C being what I've solved for, right? So I have A equals B plus NX and C equals D plus NY. And now I've done that because I know that I want to be able to have a product AC separate from a product BD. And so to do that, I've put my A and C separate from my B and D. Now, if I multiply the two equations, I multiply my left-hand sides and my right-hand sides, I end up with AC, on my left-hand side, and on my right-hand side, I end up with b plus nx times d plus ny. Distributing all of that across, I find that I have bd plus n times the quantity dx plus by plus nxy. Now, dx plus by plus nxy is an integer. And if I subtract bd from both sides, I find that I have ac minus bd equals n times an integer. Well, by the definition of congruence, I have that AC is congruent to BD mod N. There are all kinds of fun proofs that we can do with the divisibility and congruence of integers, so I hope that you're excited to dive into a few.